Welcome to Between Sleep and Science. Tonight, we drift into the quiet, overwhelming wonder of the Milky Way, the sprawling, radiant river of starlight that we call home. To look upon the Milky Way is to look into the mirror of our own origins, a cosmic autobiography written in the light of billions of suns. It is far more than a simple collection of suns or a random assembly of matter. This is a complex, living, breathing system sculpted by over 13 billion years of cosmic upheaval, violent collisions, and silent, patient evolution. This is the story of our home, a structure so vast that it humbles the very concept of existence, a grand architecture of gravity and time. For as long as humans have walked the earth, we have looked up at this hazy band of light with a mixture of fear, reverence, and awe. Before we had the tools of science, the mirrors of telescopes, and the logic of mathematics, we had the power of imagination. The ancient Greeks, gazing at the night sky over the wine-dark Mediterranean, saw it as a splash of Hera's milk across the heavens, giving us the word galaxy from the Greek gala, meaning milk. The Norse, in the frozen shadows of the fjords, saw it as the Bifrost, the burning bridge leading to the halls of Valhalla. Across the vast deserts of the world, nomads saw it as a celestial river, a ghost-white stream providing a map for their earthly travels when the shifting dunes offered no landmarks. In the Australian outback, the First Nations people looked at the dark patches within the light and saw the great emu in the sky, a spirit whose presence heralded the seasons. If these quiet wanderings bring you even a moment of calm, feel free to leave a few warm words, or tell us in the comments which city you're watching from, so we can see how far our explorations travel. You can also simply like and subscribe. Your support helps other weary hearts discover this cozy corner. And now, you don't need to do anything at all. Just settle in comfortably and let the slow, steady rhythm of deep time gently carry you away from your worries. Let the journey begin. But tonight, we move beyond myth. We step through the doorway of modern discovery into the reality of the infinite. Imagine yourself gliding slowly through this vast expanse. You are no longer bound by the heavy pull of gravity or the biological limits of your physical form. You are a consciousness drifting through the velvet dark. Shimmering dust clouds, stretching for trillions of miles, catch the faint glimmers of ancient light, turning the void into a canvas of iridescent silver and deep violet. Massive star clusters, containing hundreds of thousands of individual suns, packed together like jewels in a chest, drift like lonely, crowded islands in an infinite ocean. Each wonder we encounter on this journey was shaped across unimaginable stretches of time, where 1,000,000 years is but a single heartbeat in the life of the universe. As you settle into this exploration, feel the weight of the day dissolve. You are a passenger on a voyage through the greatest structure you will ever know. Relax, breathe deeply, and let the mind's eye open to the vastness. We are here to witness the silent work of billions of years, the slow cooling of gas, the ignition of suns, the relentless motion of dark matter, and the quiet, persistent pull of the dark, the scale of the infinite. Light's long journey through the void. To understand our galaxy, we must first confront the terrifying and beautiful reality of its scale. It is a scale that breaks the human mind if we try to hold it all at once. The Milky Way is so immense that light, the fastest messenger in existence, moving at a speed of 186,000 miles per second, a speed that could circle the Earth 7 times in a single second, requires 100,000 years just to cross its diameter from one edge to the other. Think about the speed of light in your everyday life. It slips across a room in a heartbeat, touching your eyes before you even realize it moved. It covers the distance from the moon to the Earth in just over a second. It reaches us from the sun 93 million miles away in about 8 minutes. Yet, when that same light attempts to span the breadth of the Milky Way, it seems almost sluggish, a tired traveler in a land that has no end. If you were to board a beam of light and start at the very edge of the outer spiral arms, by the time you reached the far side, humanity would have evolved, built civilizations, and perhaps vanished 10 times over. This distance is so vast, it defies the human imagination. If our entire solar system, including the orbit of Neptune, were shrunk to the size of a single coffee cup, the Milky Way would still be the size of the North American continent. The space between stars isn't truly empty, but it is open enough for light to travel freely for millennia, brushing past drifting atoms of hydrogen and microscopic grains of silicate dust. Because of this scale, when we look deep into the heart of the galaxy, we are not seeing it as it exists today. We are looking at layers of history stacked upon one another. The faint light you see from distant spiral arms began its journey long before humanity ever appeared, long before the first pyramid was built, perhaps even before the first mammal walked the earth. Every faint shimmer is a fragment of ancient time, a visual echo of a past that has long since vanished at the source. It reminds us that even the fastest thing in the universe becomes patient and gentle when measured against the size of our cosmic home. Consider the Voyager probes, humanity's most distant emissaries. They have been traveling for decades at tens of thousands of miles per hour, yet they have barely scratched the surface of the front yard of our solar system. At their current speed, it would take them over 70,000 years just to reach the nearest star, Proxima Centauri. To cross the entire galaxy, that would take them over 2 billion years. We are a tiny spark in a cathedral of light so large that our entire history is but a whisper in its halls. The invisible monarch, Sagittarius, a star, and the physics of the dark deep in the heart of the Milky Way lies a secret that dictates the fate of every star, every planet, and every drifting atom within our reach. Hidden behind impenetrable veils of freezing dust and the blinding glare of millions of crowded stars sits a monster of incomprehensible power. A supermassive black hole known to astronomers as Sagittarius A star. Its mass is 4 million times that of our Sun, yet all that weight is compressed into a space that could fit within the orbit of Mercury. Its gravity is so intense that it doesn't just pull on matter, it warps the very fabric of space-time itself, creating a gravitational well so deep that nothing, not even light, can escape once the event horizon is crossed. For decades, this monarch remained invisible, shrouded in mystery. We could not see it, for it swallows the very light that would reveal it. We only began to understand its nature by watching the stars that dare to orbit near the core. These stars are forced into frantic, looping paths, moving at several percent of the speed of light, millions of miles per hour, whipped around by the invisible mass at the center. While its influence is gentle and anchoring at a great distance, holding the galaxy together in its rotation, near the core, it becomes an overwhelming force of destruction and creation. Massive gas clouds are stretched and twisted into glowing spirals, heating up to millions of degrees as they are compressed and torn apart, falling towards the dark center. Though the black hole itself is silent and dark, the region around it pulses with violent activity, emitting flares of X-rays and radio waves that act as the heartbeat of the galaxy. This hidden heart anchors the Milky Way, giving shape to its rotation and binding billions of stars together in a grand gravitational ballet that has lasted for eons. It is a place where the laws of physics are pushed to their breaking point, a reminder that at the center of all this light there is a core of absolute silent darkness. If you were to approach this monarch, time itself would begin to fail. Due to the intense gravity, a clock near the event horizon would tick much slower than a clock on Earth. Minutes spent near the black hole could translate to years passing in the outside world. This is the reality of our galactic center, a place where space and time are not fixed but are fluid, shaped by the crushing weight of an unseen giant. A history of cosmic consumption, the chronicles of galactic feast. The Milky Way we see today, with its elegant spiral arms and glowing core, carries the deep scars of a predatory and violent past. It is not a static object. It is a survivor of a long, brutal history of mergers and acquisitions. Long ago, in the early days of the universe, our galaxy was much smaller, but it was hungry. In a series of events known as galactic cannibalism, several large companion galaxies drifted too close, captured by the Milky Way's superior gravity. Over millions of years, these companions were gradually torn apart by powerful tidal forces, their structures shredded, their stars scattered like dust. Evidence of this ancient feast remains today in what we call the galactic halo, the vast spherical region surrounding the main disk. Here, astronomers have found ghost stars, entire populations of stars that move in directions contrary to the rest of the galaxy. They carry chemical fingerprints that do not belong here. They contain different ratios of heavy elements than the stars born in our disk, proving they were born in a different environment, under the light of a different sky, before being absorbed into our own structure. One of the most significant of these vanished giants was a galaxy we now call Gaia Enceladus. When it collided with the young Milky Way 10 billion years ago, the impact was so great that it sent shock waves through the system, triggering a massive burst of star formation and thickening the galactic disk into the shape we see tonight. It serves as a stark reminder that the beauty of the cosmos is often built upon the ruins of what came before. The vanished giants of the past now shine as part of our own celestial home, their identities lost to all but the most sensitive instruments of modern science. We are the inheritors of these lost worlds, our own sun, likely moving through the debris of 1,000 dead systems. The Galactic Neighborhood, a community of satellite elders. Encircling the grand disk of the Milky Way is a quiet, often overlooked community of smaller satellite galaxies. There are dozens of them, ranging from the well-known large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere, to tiny, ultra-faint dwarf galaxies that contain only a few thousand stars and are almost entirely made of dark matter. Each one is a time capsule, preserving the memories and the chemistry of a much younger, simpler universe. These companions drift in graceful, long-duration orbits that take hundreds of millions of years to complete. Though small in comparison to the giant spiral they orbit, they play a vital role in our galaxy's life cycle. Their slow passage tugs at our outer halo, like a moon pulling on a terrestrial ocean, stirring subtle waves that ripple through the dark matter envelope and the outer gas clouds. These interactions can trigger the collapse of gas clouds in our own spiral arms, sparking the birth of new suns. Some of these companions, like the Sagittarius dwarf spheroidal, have already begun their final descent, shedding delicate streams of stars that wrap around the Milky Way like ancient golden threads. Studying them is like studying the elders of a great family. They hold the keys to understanding how the Milky Way became the majestic structure it is today. They remind us that no galaxy, no matter how large, exists in total isolation. We are part of a local group, a neighborhood of travelers moving together through the void, bound by the invisible ties of gravity. The Large Magellanic Cloud, specifically, is on a collision course with us. In about 2 billion years, it will merge with the Milky Way, bringing a fresh supply of gas and triggering a new era of stellar fireworks. The Sun, a high-speed traveler in the galactic disk. In our daily lives, we view the Sun as a steady, still anchor, a warm and familiar constant in our sky that marks the passage of our days and years. But this is a trick of perspective, a comfort born of our tiny scale. In reality, the Sun is a high-speed traveler, hurtling through the galaxy at nearly 500,000 miles per hour. It is moving faster than any bullet ever fired, sweeping our entire solar system. Every planet, every moon, every asteroid, and every drifting speck of dust, along on a grand, sweeping voyage around the galactic center. Everything you have ever known, every person who has ever lived, every empire that has risen and fallen is currently riding this incredible motion. The Sun follows a curved path, guided by the collective gravity of the hundreds of billions of stars that lie ahead of us. Even though we cannot feel this motion, it is always happening, determining the long-term future of our corner of the universe. As we journey through the disk, we encounter varying environments: thin clouds of interstellar gas, faint radiation fields from distant supernovas, and shifting gravitational currents. Our Sun takes about 230 million years to complete a single trip around the center, a period known as a galactic year. The last time we were in this exact spot in the galaxy, dinosaurs were just beginning to walk the Earth. The last time before that, life was just venturing out of the oceans. This silent voyage has lasted for 4.5 billion years, and it will continue for billions more. The thought that our familiar star is actually a restless traveler in an enormous, never-ending orbit invites a quiet sense of awe. We are passengers on a ship that never docks, moving through a sea of stars that has no shore, carried by currents we are only beginning to map. Stars born of ice, the paradox of cold creation. When most people imagine the birth of a star, they picture scenes of intense heat, raging flames, and blinding energy. They think of a cosmic furnace, a place where fire reigns supreme. But the truth of stellar creation is far stranger and more poetic. Stars do not begin in fire. They begin in the deep, absolute cold of molecular clouds. These clouds, often called stellar nurseries, are colder than anything found naturally on Earth, often hovering just a few degrees above absolute zero. In these places, fire is a physical impossibility. These clouds are made of hydrogen gas and microscopic dust, drifting through the Milky Way like giant, dark ghosts. They are so dense and cold that they block the light of the stars behind them, appearing to our eyes as holes in the sky. Inside these frozen cradles, the only force that matters is gravity. Gravity does the work that heat cannot. It gathers the cold material, pulling it together into dense, dark pockets known as Bock globules. As these pockets contract, they begin to warm, not from fire, but from the sheer pressure of their own mass. Imagine a crowd of people being squeezed into a small room. The friction and the pressure create heat. Over unimaginable stretches of time, the temperature at the center of these pockets climbs from near absolute zero to millions of degrees. Only when the heat becomes truly unbearable does nuclear fusion finally ignite, the process where atoms are forced together to release energy. In that one glorious moment, a silent, frozen knot of dust is transformed into a shining sun. It is a cosmic secret. The most brilliant light in the universe is born in the darkest, coldest places, proving that creation often begins in total stillness. Living in a bubble. The ghostly scars of ancient giants. We often think of space as a uniform vacuum, an empty stage for the stars to dance upon. But we actually live inside a giant cavity carved out of the interstellar medium. This is the local bubble, a vast region of space, hundreds of light years wide, that surrounds our solar system. It is a scar on the face of the galaxy, a testament to the power of stars that died long before we were born. Long before humans existed, powerful stars near our region of the galaxy lived fast, violent lives, and ended in spectacular explosive deaths known as supernovas. Those supernovas acted like celestial snowplows, pushing away enormous amounts of gas and dust and clearing out a wide area of space. Today, we drift comfortably within this airy region, which is filled with extremely thin, million-degree gas created by the shock waves of those ancient explosions. The material here is far less dense than the gas found elsewhere in the Milky Way, allowing our sun and planets to move through space as if passing through a quiet, empty room left behind by violent events of the past. The edges of this bubble are shaped like walls of cooler gas, where the remnants of those explosions finally slowed down. Realizing that our entire home sits within the graveyard of long-vanished stellar giants brings a soft and humbling perspective to our place in the galaxy. We are the beneficiaries of ancient cataclysms, living in a space cleared by the deaths of stars that were far greater than our own. We are surrounded by the quiet echoes of a violent past that made our peaceful present possible. The endless feast. A galaxy in constant, relentless motion. Galaxies may look peaceful and static from our distant vantage point, like ornaments hung in the night sky. But they are dynamic, ever-changing structures that interact, merge, and consume one another over immense stretches of time. The Milky Way is no exception to this rule of cosmic evolution. It is a living entity, currently in the process of drawing in several smaller dwarf galaxies that orbit nearby. This is a relentless process of integration that has happened many times before and will happen many times again. As these smaller systems fall toward us, Caught in our gravitational web, their stars are stretched into long, delicate ribbons that wrap around our galaxy like shimmering threads. These tidal streams are the remains of galaxies being digested. Bit by bit, their stars, their globular clusters, and their mysterious dark matter become part of the Milky Way itself. This process helps explain why we find old star clusters in unusual places, and why some stars in our neighborhood move with such strange velocities. Even now, the Sagittarius dwarf galaxy is being pulled apart as it falls toward our galactic disk, its stars contributing to our mass even as its individual identity fades. The idea that our galaxy is shaped by a long history of relentless cannibalism feels both strange and fascinating. It reminds us that even structures as vast as galaxies are still subject to the quiet, irresistible pull of gravity, constantly reshaping themselves through the consumption of their neighbors. In about 4 billion years, this process will reach its climax when the Milky Way collides with the Andromeda Galaxy, turning both into a single, massive elliptical galaxy. Ancient survivors, stars from the dawn of the first light. The Milky Way is a repository of history, holding stars that formed long before the Earth, or even the Sun, ever existed. Some of these stars are more than 13 billion years old, nearly as old as the universe itself. These ancient survivors provide us with a direct glimpse into the early days of the cosmos, acting as stellar fossils that carry the chemical signatures of the first generations of matter. These old stars are fundamentally different from our Sun. They contain very few heavy elements like iron, gold, or carbon, because those elements had not yet been created in large amounts by the supernovas of the past. When these stars were born, the universe was made almost entirely of hydrogen and helium. Their light is simpler, their atmospheres are purer, and their stories are much, much longer. Many of these survivors drift in the galactic halo, a sparse, spherical region that surrounds the main disk of the Milky Way. They move on long, eccentric orbits that take them high above the spiral arms, looking down upon the rest of the galaxy like ancient sentinels. Observing them allows astronomers to study the conditions of the early universe in a quiet and direct way, bypassing the interference of younger, more complex systems. These ancient suns have burned steadily for billions of years, holding secrets from a time when the galaxy was still new, formless, and filled with the raw energy of the Big Bang. Their existence adds a deep sense of continuity to our story, a reminder that the light we see tonight has roots that reach back to the very beginning of everything. The soft chorus of the unseen, red dwarfs and the hazy glow. When you look up at the Milky Way on a perfectly clear, dark night, you see a glowing band of hazy light stretching across the sky, a celestial path that has inspired every civilization. Much of that beautiful glow does not come from the bright, prominent stars you can name, like Sirius or Vega. Instead, it comes from trillions of stars that are far too faint for even the most powerful telescopes to see individually. These are the red dwarfs and low-mass suns that make up the vast majority, nearly 75% of our galaxy's population. Though they are individually dim, their numbers are so vast that their combined light forms the soft, luminous background that fills the disk of the galaxy. This light is scattered and softened by clouds of gas and dust, giving the Milky Way its signature misty appearance. Even though these stars are invisible to us as separate points of light, they contribute significantly to the total mass and gravitational structure of the galaxy. They are the silent majority, the small and steady suns that guide the motion of the brighter, more famous stars. Some of them have burned for 10 billion years and will continue to burn for 1 trillion more, long after our sun has faded and the spiral arms have changed their shape. The idea that the galaxy shines with the collective breath of countless unseen suns creates a gentle feeling of mystery. The light we see is not just the glow of a few bright leaders, but the soft, enduring chorus of multitudes whispering across the reaches of space, a reminder that even the smallest lights, when gathered together, can illuminate the dark. Rogue planets, the lonely, cold travelers of the deep void. Not all planets are fortunate enough to belong to a star. In the vast, dark spaces between the suns of the Milky Way, there are millions, perhaps billions of worlds that move freely through the void, drifting alone through the eternal night. These are the rogue planets, or nomad worlds, planets that were likely born in traditional solar systems, but were later cast out by violent gravitational interactions with larger planets or passing stars during the chaotic early years of their formation. Without a sun to warm them or provide a predictable orbit, these planets travel through the galaxy in a state of deep, absolute cold. Their surfaces are likely frozen solid, locked in a permanent, starless twilight. Yet, some of these lonely worlds might hide warm interiors, powered by the decay of radioactive elements or the intense pressure of their own cores. Some might even have subsurface oceans, protected by miles of ice, where life could theoretically survive in the dark. The idea of a planet wandering alone through the galactic disk creates a haunting sense of quiet beauty. They do not follow the rules of our solar system. They move on long, solitary paths shaped only by the gravity of the galaxy itself. They may pass near distant stars, slip through crowded clusters, or eventually disappear into the dark reaches of the galactic halo. Thinking of these silent travelers invites a calm sense of wonder. In the enormous gaps between the stars, entire worlds glide unseen, solitary and patient, carrying their own hidden stories through the cosmic night, ambassadors of systems that no longer hold them. The scorching halo, the invisible atmosphere of our galaxy. We often imagine the Milky Way as a flat, two-dimensional disk, a spinning plate of stars. But it is actually enveloped in a massive, three-dimensional halo of gas that stretches far into intergalactic space, reaching hundreds of thousands of light-years. This gas is not like the cold clouds where stars are born. It is incredibly hot, heated to temperatures of millions of degrees, far hotter than any flame found on Earth. This gas is so energized that it emits a faint glow of X-rays, invisible to the human eye, but detectable by our most sensitive orbital satellites. Though this halo is extremely thin, with fewer atoms per cubic meter than the best vacuum we can create on Earth, its total mass is enormous, potentially equaling the mass of all the stars in the galaxy combined. It acts as a vast reservoir of matter, a celestial atmosphere that surrounds and protects the entire galaxy. This hot gas is thought to be a leftover from the early formation of the Milky Way, as well as the result of ongoing activity from supernovas that push material out of the disk in what astronomers call galactic fountains. Over millions of years, some of this gas may cool and fall back into the galaxy, fueling the birth of new generations of stars. The halo is a reminder that the Milky Way is a layered and intricate structure, with components that reach far beyond the visible stars, enveloping everything we know in a quiet, searing, and protective embrace. It also contains the mysterious dark matter, invisible matter that provides the gravity needed to keep the galaxy from flying apart. Radio echoes, the ghostly, persistent voices of dead stars. Across the vast reaches of the Milky Way, ancient explosions have left behind signals that travel farther and last longer than the visible light from their shattered remains. These signals appear to us as radio waves, low-frequency pulses that are gentle in tone but incredibly powerful in their reach. When a massive star dies in a supernova, the explosion sends shockwaves rippling through the interstellar medium at thousands of miles per second, like a stone thrown into a still pond. These shockwaves energize the surrounding gas, causing it to hum with radio frequencies that can cross the entire galaxy without being blocked by the thick clouds of dust that obscure our visual view. Even thousands of years after the visible flash of the explosion has faded into darkness, the radio glow remains, drifting quietly through the spiral arms. Astronomers use sensitive radio telescopes to trace these faint echoes, mapping the locations of old remnants that are hidden deep inside dusty regions where no light can escape. Each ripple carries information about the force of the long-gone explosion and the materials it released into space. The iron in our blood, the calcium in our bones, and the oxygen we breathe. In this soft radio light, the galaxy speaks of its violent past, whispering memories of stars that lived brightly and ended in dramatic silence, ensuring that their legacy lives on in the very fabric of the cosmos. The impossible density, the crushing world of neutron stars. Among the most terrifying and fascinating objects in the Milky Way are neutron stars. These are the collapsed cores of massive stars that have reached the end of their lives and exploded. What remains is an object so dense that the laws of physics as we know them begin to break down, entering a realm of extreme reality. A neutron star contains more mass than our Sun, yet all that weight is squeezed into an object no larger than a city, perhaps 12 miles across. The matter within a neutron star is so tightly packed that atoms themselves cannot survive. The space between the nucleus and the electrons is crushed out of existence, and protons and electrons are forced together to form a solid mass of neutrons. If you could somehow take a single teaspoon of this material, something no human could ever survive doing, as the gravity alone would crush you instantly, it would weigh more than 5 billion tons, or roughly the weight of a mountain. This unimaginable density reshapes the very environment around the star. Gravity is so intense that light trying to escape is bent back into circles, and the magnetic fields generated are trillions of times stronger than anything we can produce on Earth. These strange remnants cool slowly over millions of years, gradually fading as they release their trapped heat. They remind us that the Milky Way is a place of extremes, where the familiar matter of our world can be compressed into states that defy all logic, turning a sun into a single, massive atomic nucleus drifting through the dark. Star streams, the golden, winding rivers of the halo. Throughout the sparse, lonely reaches of the galactic halo, long, delicate chains of stars drift together along gentle, sweeping arcs. These are the star streams, the beautiful and tragic remains of smaller galaxies and star clusters that were once whole, independent systems with their own unique structures. Over eons, the Milky Way's superior gravity pulled them apart, stretching them into long filaments that follow the original orbits of the lost systems, like ribbons caught in a breeze. Though they are faint and difficult to find, these streams act as a perfect, high-fidelity record of the Milky Way's history of interactions. By studying their motion and the chemistry of their stars, astronomers can rewind the clock of the universe, reconstructing the exact events that led to their destruction. Some of these streams curve high above the galactic plane, while others flow quietly through the dense spiral arms, hidden among the local populations like ghosts in a crowd. These delicate ribbons of light also help scientists map the invisible distribution of dark matter that surrounds our galaxy, as their paths are bent and shaped by the gravity of things we cannot see. In a quiet, persistent way, star streams show us that the Milky Way is constantly evolving, carrying the memories of ancient encounters stretched across the sky like soft, golden reminders of a long and complicated past. They are the artifacts of a time when the galaxy was still building itself, one neighbor at a time. The constant birth, a galaxy that never truly sleeps. Despite its ancient age of over 13 billion years, the Milky Way is far from a finished structure. It is not a stagnant monument. It is a place of constant renewal where new stars ignite every single second. In the cold, shadowed depths of molecular clouds scattered throughout the spiral arms, the process of creation never truly stops. Gravity is always at work, silently pulling gas into dense pockets that will eventually become suns. This process happens so frequently across the vast disk of the galaxy that, on average, several new stars are born every year, meaning at any given moment, a new light is likely flickering into existence somewhere in the dark. Some of these newborns are tiny red dwarfs that will burn quietly for trillions of years, outlasting even the memory of our solar system. Others are massive blue giants that will burn with a fierce, blinding intensity for only a few million years before ending in spectacular explosions. The locations of these births are shaped by the flow of magnetic fields and the leftover material from older generations of stars, creating a cycle of cosmic recycling. Light from these newly formed clusters gradually clears away the surrounding dust, revealing brilliant jewels of light against the dark background. The continuous birth of stars is the engine that keeps the Milky Way alive and dynamic, ensuring that even as old suns fade into darkness, new sources of light and hope are always appearing to take their place. Rapid rotators, the stars that challenge the spherical. In the diverse and strange population of the Milky Way, there are stars that rotate with such astonishing speed that they challenge our basic understanding of what a star should look like. While our Sun takes nearly a month to complete a single rotation, these rapid rotators spin on their axes in just a few hours. Their equators move at hundreds of kilometers per second, so fast that if it weren't for the immense pull of their own gravity, they would literally tear themselves apart, scattering their plasma into the void. This incredible spin causes the stars to bulge outward at their equators, forming flattened egg-like shapes, or oblate spheroids, rather than perfect spheres. This distortion creates strange and beautiful physical effects. The poles of the star, being closer to the core and under more pressure, are significantly hotter and brighter than the equator, a phenomenon known as gravity darkening. This rapid rotation also generates powerful magnetic fields and affects how the star burns its nuclear fuel, often shortening its lifespan and causing it to eject material in massive disks. Observing these stars helps astronomers understand the limits of stellar physics and the balance between the outward push of motion and the inward pull of stability. They show us that even the most massive and stable-looking objects in the galaxy can be shaped and distorted by the simple, relentless force of rotation, turning a sun into a spinning top of fire. Voids and cavities, the gaps in the starlight landscape. The Milky Way is not a uniform or solid structure. It is a Swiss cheese of space, filled with enormous cavities and vast stretches of empty space. These voids can span hundreds of light years, leaving behind pockets of thin, hot gas inside the otherwise crowded spiral arms. Most of these cavities were carved out by the collective energy of OB associations, groups of massive hot stars that lived fast and died young. Their intense stellar winds, moving at millions of miles per hour, and the shock waves from their eventual supernovas pushed the surrounding interstellar gas away, hollowing out bubbles that merged over time into even larger voids. Though these regions contain far fewer particles than their surroundings, they are not truly empty. They are influenced by the gentle pressure of nearby gas and the gravitational pull of the galaxy. Studying these cavities helps astronomers understand how energy flows through the system and how the death of one generation of stars clears the path and the space for the next. They reveal where massive clusters once lived and how their activity influenced the environment for millions of miles. They remind us that the galaxy is shaped as much by what is missing as by what is present. A complex landscape of bright birthplaces and quiet, hollowed-out gaps that tell the story of lives lived at the extreme. Diamond worlds, the glittering, hidden secrets of cosmic chemistry. Among the many strange and exotic planets in the Milky Way, there is a class of worlds that sounds more like a dream or science fiction than physical reality. These are the carbon planets, worlds where the chemical makeup of the original protoplanetary disk was rich in carbon and poor in oxygen. In these systems, the interior of the planet may form layers of solid diamond that stretch for thousands of miles. Under the intense pressure found deep within a planet's mantle, carbon atoms can be squeezed into crystalline structures, creating massive shells of diamond. The surfaces of these worlds might be dark and rocky, perhaps covered in layers of graphite, tar, or soot. But below lies a landscape of glittering, crystalline beauty. These diamond worlds may orbit close to their stars or drift farther away, but their existence shows that the chemistry of the galaxy is incredibly varied and creative. They reveal that planets can differ dramatically from the rocky and gaseous worlds of our own solar system, offering a quiet sense of wonder at the creative power of the elements. In the Milky Way, the treasures of the universe are not always found in the light, but sometimes hidden deep beneath the crust of an alien world, waiting in the dark for a light that may never reach them. They are a reminder that the same carbon that makes up the life in our bodies can, under different stars, build an entire world of gems. Magnetic monsters, the terrifying reign of the magnetars. Of all the rare and extreme objects that inhabit our galaxy, perhaps none are as terrifying or as powerful as magnetars. These are a special type of neutron star, the remnants of a supernova, with magnetic fields that are a quadrillion times stronger than Earth's. To put that in perspective, if a magnetar were located halfway to the Moon, its magnetic pull would be so strong that it would instantly wipe the data from every credit card on Earth and literally tear the iron atoms out of your blood from 100,000 miles away. These fields are so intense that they can actually distort the shape of atoms, stretching them into long, needle-like cylinders and changing the way chemistry functions. Magnetars occasionally experience starquakes, where the immense magnetic stress causes the star's solid crust, made of the densest matter in the universe, to crack. This release of energy produces a flare so powerful that it can briefly outshine every other star in the Milky Way combined, emitting more energy in a fraction of a second than the Sun does in 100,000 years. Though they are only about 15 miles across, their influence is felt across the entire galaxy. Studying these magnetic monsters helps scientists understand the behavior of matter and energy under the most extreme conditions imaginable, where gravity and magnetism reign supreme. They stand as a reminder that the Milky Way is home to phenomena that push the very boundaries of what is possible in the physical universe, turning a tiny star into a cosmic magnet of nightmare proportions. Binary suns, the worlds of two shadows and twin dawns. Across the Milky Way, the majority of stars do not live solitary lives like our Sun. They are born in pairs, trios, or even larger groups, orbiting a common center of gravity in a complex orbital dance. For a long time, we wondered if such chaotic systems could host planets, or if the competing pulls of gravity would tear them apart. Today, we know the answer is a resounding yes. There are circumbinary planets, worlds that orbit two suns at the same time, following graceful, complex paths shaped by the combined pull of both stars. If you were to stand on the surface of such a world, your sky would be unlike anything imaginable on Earth. You would see two suns of different colors and sizes, perhaps a large red giant and a small, brilliant blue star, rising and setting at different times. Sometimes, both suns would be in the sky together, creating a world of double shadows and double warmth. Other times, one would rise just as the other set, leaving the planet in a state of perpetual, colorful twilight. The climate on these worlds would be highly variable, shifting as the distance between the planet and its two suns changed throughout the year. These systems reveal the incredible flexibility and resilience of planetary formation, showing that even in the chaotic environment of a double star system, nature can still build stable and beautiful worlds. They are the Tatooines of the real universe, proving that our imagination is often just a preview of the reality waiting among the stars. The mystery of antimatter, a shadow galaxy. In the core, deep near the heart of the Milky Way, in the regions where gravity is strongest and radiation is most intense, astronomers have discovered traces of something truly mysterious and unsettling: massive clouds of antimatter. Antimatter is the mirror image of normal matter. It has the same mass but the opposite electrical charge. When a particle of matter meets its antimatter twin, they instantly annihilate in a flash of pure, perfect energy. The presence of these antimatter clouds near the galactic center is a profound mystery that challenges our understanding of the universe. They are detected by the specific high-energy gamma radiation produced during these annihilations. The origin of this material is still being debated in the highest halls of science. It may come from the intense magnetic activity around the central black hole, from the decay of mysterious dark matter particles, or from the rapid, violent death of massive stars. Because antimatter is so difficult to create and even harder to preserve in a universe made of matter, its existence in large quantities suggests that the center of the Milky Way is a place of high-energy processes that we are only beginning to understand. These subtle signals show that our galaxy's core is not just a place of gravity and light, but a high-stakes laboratory for the most fundamental and exotic forces in the universe, where the very building blocks of reality are being created and destroyed in the dark. Galactic ghosts. The tragic persistence of tidal streams. Stretching across the vast dark sky of the Milky Way are long, delicate trails of stars that move like ghostly ribbons through the void. These are the tidal streams, the beautiful and tragic remains of smaller galaxies and star clusters that ventured too close to our own billions of years ago. The Milky Way's gravity acted like a giant tidal force, similar to how the moon pulls on Earth's oceans, stretching these systems until they were shredded into long, thin filaments of stars that can span the entire sky. Each stream carries the unique memory of a galaxy that once had its own shape, its own history, and its own family of planets. By studying the motion and composition of these stars, astronomers can rewind the clock of the universe, reconstructing the size, shape, and even the dark matter content of the original lost systems. Some streams curve high above the galactic plane, while others flow quietly through the dense spiral arms, invisible to all but the most sophisticated digital surveys. These streams also act as tracers for the invisible distribution of dark matter that surrounds our galaxy, as their paths are bent and shaped by the gravity of things we cannot see. They remind us that the Milky Way is a graveyard of galaxies, a majestic structure built on the remnants of travelers who came before us, and that our current peace is built on a history of ancient celestial disruption, the cosmic waltz, binary mergers, and luminous novas. In many parts of the Milky Way, stars are locked in a gravitational dance that can last for billions of years. These binary pairs circle each other, sometimes so closely that their outer atmospheres touch, exchanging heat and plasma in a searing embrace. Over time, as they exchange energy through gravitational waves, stellar winds, or tidal friction, their orbits can slowly shrink, bringing them closer and closer together with every passing century. Eventually, the dance ends in a final, inevitable collision. When two stars finally merge, the event produces an enormous, blinding burst of light and energy, a luminous red nova. This collision creates a single, larger and much brighter star, while enriching the surrounding space with heavy elements forged during the violent union of two suns. These mergers are a vital part of stellar evolution, helping us understand how rare and massive stars are formed and how the chemical makeup of the galaxy changes over time. Though the process takes an immense amount of time to unfold, The idea that two suns can slowly fall toward one another until they become one adds a poetic sense of motion and drama to the Milky Way. Even in the seemingly static night sky, quiet celestial waltzes are unfolding, moving toward a final, brilliant embrace that will light up the darkness for millions of miles. Alien weather, rains of molten glass and liquid metal. Among the thousands of exoplanets discovered in the Milky Way, some experience weather patterns that are entirely beyond our comprehension, making the most violent earthly storms look like gentle breezes. On certain hot Jupiters, massive gas giants that orbit very close to their parent stars, the temperatures are so extreme, reaching thousands of degrees, that metals like iron and aluminum actually evaporate into the atmosphere as a gas. When these metallic vapors move to the cooler, night side of the planet, they condense into droplets and fall as shimmering metallic rain. On other worlds, strong winds, moving at thousands of miles per hour, whip molten droplets of silica, the stuff of sand and rock, across the sky, creating storms of liquid glass that move sideways with terrifying force, shredding anything in their path. The surfaces of such planets are not places where life could exist as we know it, but they are places of incredible, alien beauty and power. These extreme conditions occur because of the intense radiation these worlds receive and their unique chemical compositions. They remind us that weather is not limited to clouds and storms of water. In the vast, creative diversity of the Milky Way, even the rain can be made of the very stuff of the stars, turning a planet into a glittering, dangerous jewel of heat and light. The intergalactic wanderer, stars without a home or a sky. Not every star that is born in the Milky Way stays here. In the chaotic and violent history of the galaxy, some stars have been violently ejected, sent hurtling into the empty, freezing space between galaxies. This can happen when a star passes too close to the supermassive black hole at the center and is slingshot out of the system, or when its binary companion explodes in a supernova, abruptly breaking the gravitational bond that held them together. Once thrown free, these stars become lonely wanderers, drifting through intergalactic space at millions of miles per hour. They shine just like any other sun, but they have no neighbors, no galaxy to call home, and no night sky filled with the comfort of other stars. Their journeys take them far from any source of warmth or light, into the cold, dark reaches of the cosmic void between the great islands of the universe. The Milky Way has likely lost millions of stars this way over its long life. Studying these runaway or hypervelocity stars helps astronomers understand the extreme gravitational events that can occur in the heart of a galaxy. They are the solitary outcasts of the cosmos, carrying their light into the eternal night, far from the bustling, crowded spiral arms of their birth, destined to drift forever in the dark. The elders of the halo, globular clusters and ancient light, scattered throughout the sparse, lonely reaches of the galactic halo, are globular clusters, dense, ancient spheres of stars that are among the oldest structures in the entire universe. A single globular cluster can contain up to 1 million stars, all packed into a space only a few dozen light-years wide, held together by their mutual gravity. Many of these clusters are older than the Sun, older than the Earth, and perhaps even older than the spiral disk of the Milky Way itself. These stars are the survivors of the first generations of stellar birth, formed before the galaxy had enriched itself with heavy elements. If you were to live on a planet inside a globular cluster, your night sky would never be dark. It would be filled with thousands of brilliant suns, all crowded together in a blinding, beautiful display of light. These clusters orbit outside the main disk of the galaxy, moving on long looping paths that take them far from the gas and dust of the spiral arms. Observing them helps scientists reconstruct the very beginning of our galaxy's history and the conditions of the early universe. Their age gives them a quiet dignity. They are the ancient, stoic guardians of the Milky Way, floating through a system that has changed dramatically since they first ignited 13 billion years ago, witnesses to the birth and death of everything we know. Pulsars, the precise, rhythmic lighthouses of the galaxy. Some of the most extraordinary and useful objects in our galaxy are pulsars, rapidly rotating neutron stars that emit focused beams of electromagnetic radiation from their magnetic poles. As the pulsar spins, these beams sweep across space like the focused light of a lighthouse. If the beam happens to point toward Earth, we see a pulse of energy that repeats with incredible, machine-like precision. The timing of these pulses is so regular that when they were first discovered in the 1960s, some scientists seriously wondered if they were signals from an advanced alien civilization, naming the first one LGM-1 for Little Green Men. Today, we know they are the remnants of massive stars. Some pulsars spin several times per second. Others, known as millisecond pulsars, rotate hundreds of times in that same span, faster than the blades of a blender. Their steady pulses are used by astronomers as a galactic GPS to map the structure of the galaxy, detect the ripples of gravitational waves, and test the limits of Einstein's theory of general relativity. Pulsars are the precision timekeepers of the Milky Way, sending their rhythmic, ancient signals through the darkness and allowing us to study the most distant and dusty regions of the galaxy with a clarity that light alone cannot provide. They are the metronomes of the cosmos, marking the passage of time in the deep dark. The radiant clouds of the core, a chaotic, high-speed dance. Near the heart of the Milky Way, in the region surrounding Sagittarius A, the environment is far from the peaceful stillness we see from Earth. It is a restless, violent zone of intense radiation, powerful magnetic fields, and gas clouds that move at speeds that defy human intuition. These clouds orbit close to the central black hole, where the gravitational pull is at its most extreme and unforgiving. Some of these clouds race around the center at hundreds of miles per second, tracing elongated, chaotic loops that shift with the tides of gravity. The turbulence in this region is so high that the clouds are constantly being stretched, compressed, and twisted into strange filament-like shapes that look like ribbons of fire in the dark. Thick layers of interstellar dust block this view from our eyes, but with infrared and radio telescopes, we can see the gas rushing and colliding in a complex, spiraling flow. Tracking these movements is how we calculate the mass of the central black hole and understand the invisible structures of the galactic core. The energy and pace of this environment are a stark contrast to the calm appearance of the night sky, revealing that the heart of our home is a place of incredible dynamic power, where matter is accelerated to its limits and space itself is bent to the will of the monarch. Water worlds. the endless global oceans of the Milky Way. Among the staggering diversity of worlds in our galaxy, there is a class of planets that challenges our definition of a habitable world. These are the water worlds, or ocean planets. Planets that are believed to be dominated by water in quantities that dwarf the oceans of Earth. On these worlds, there are no continents, no islands, and no dry land. Just a global planet-wide sea that can reach hundreds of miles deep. Under the intense pressure found at the bottom of these massive oceans, water can take on exotic states that are not found naturally on Earth, forming layers of high-pressure ice that remain solid even at high temperatures. These planets may have thick atmospheres that trap heat, creating layers of superheated water and steam beneath their clouds. Some of these worlds orbit close to their stars, where their oceans are warm and potentially teeming with alien life. Others drift in the cold outer reaches of their systems, where they are covered by a crust of ice miles thick. Observing them helps astronomers understand how planets form from different materials and how water, the essential ingredient for life, is distributed across the galaxy. Imagining an entire world shaped and defined by water, a place where the horizon is a never-ending line of waves, brings a sense of quiet wonder to the Milky Way. They are the maritime frontiers of the cosmos, global seas waiting for a shore. Ultra-cool dwarfs, the quiet, ember-like suns of the dark. Not every star in the Milky Way burns with the fierce, blinding heat of our sun or the explosive energy of a blue giant. Many stars are so cool and faint that their temperatures barely exceed those of a domestic oven or a giant planet. These are the ultra-cool dwarfs, stars that emit most of their light in the infrared spectrum, making them nearly invisible to the unaided eye. Despite their small size and low temperature, they are true stars, powered by a steady, slow nuclear fusion of hydrogen deep within their cores. Because they burn their fuel so efficiently and slowly, they have lifespans that can last for trillions of years, thousands of times longer than the current age of the universe. Studying these stars helps astronomers understand the lower limits of stellar formation and the boundary between stars and planets. Some of these cool suns host their own planetary systems, such as the famous TRAPPIST-1 system, where multiple Earth-sized worlds orbit in a compact arrangement. Life on a planet orbiting an ultra-cool dwarf would experience a world of dim, reddish light, where the sun is a large, dark red ember in the sky. These stars are the quiet, persistent survivors of the Milky Way, the embers that will still be burning long after the brighter stars have gone out. A reminder that in the galaxy, slow and steady truly does win the race of time. Stellar bow shocks, the graceful waves of runaway suns. As some stars move rapidly through the galaxy, far faster than the surrounding gas and dust, they encounter the interstellar medium in a dramatic, high-speed collision. This interaction creates a stellar bow shock, a curved bow-shaped shock wave similar to the wave formed by the prow of a boat moving through still water. This shock compresses and heats the gas in front of the star, causing it to glow in infrared or visible light as a graceful, luminous arc. The shape, brightness, and size of the bow shock depend on the star's speed, the strength of its stellar wind, and the density of the material it is plowing through. These structures act as cosmic speedometers, revealing important information about the star's history and its motion through the galaxy. Some bow shocks stretch across light years, forming beautiful, glowing walls that mark the star's journey through the void. Observing them helps astronomers track runaway stars, stars that have been ejected from their birthplaces, and understand how high-speed interactions shape the environment of the Milky Way. These luminous curves are the artistry of motion, a visual record of a sun's lonely, fast-paced travel across the galactic landscape. Hypervelocity stars, the slingshot travelers of the core. Most stars in the Milky Way follow stable, predictable orbits shaped by the galaxy's mass, moving in the grand circle of the spiral arms. However, there is a rare and mysterious group of stars that travels at extraordinary speeds, millions of miles per hour, fast enough to eventually leave the Milky Way entirely and never return. These are the hypervelocity stars. These stars are usually launched by the most powerful gravitational engine in the galaxy, the supermassive black hole at the center. When a binary star system passes too close to Sagittarius A star, the black hole's gravity can capture one star and slingshot the other outward with an incredible burst of kinetic energy. Other hypervelocity stars are released when their companion star explodes in a supernova or through chaotic interactions in crowded star clusters. Once accelerated, these stars move on long, straight paths outward, slipping through the spiral arms like ghosts and drifting into the quiet, empty regions of the halo before finally breaking free into intergalactic space. They are the ultimate runaways, carrying the secrets of the galactic center into the eternal dark between the galaxies. Studying them helps astronomers understand the extreme conditions and violent physics that occur at the heart of our home, where gravity can turn a star into a cosmic projectile. Plasma clouds, the energized, glowing veins of space. The space between the stars is not just empty vacuum or cold gas. It is often filled with clouds of energized plasma, gas where the electrons have been stripped from their atoms, leaving behind a sea of charged particles. These plasma clouds respond strongly to the magnetic fields that thread through the Milky Way, behaving in complex and unpredictable ways. They can twist into long, slender filaments, ripple like waves on a pond, or glow with a soft, ethereal light generated by electrons spiraling through magnetic structures. Many of these plasma clouds are created by the intense radiation of massive stars or the shock waves of supernova explosions, which pump energy into the surrounding medium. Others are shaped by the turbulence of the galactic rotation itself. Studying these regions provides vital insight into the magnetic environment of the Milky Way, which is otherwise invisible to our eyes. Plasma clouds act as the nervous system of the galaxy, carrying magnetic energy and guiding the path of cosmic rays, high-energy particles that travel at nearly the speed of light. They reveal that the spaces between the suns are not empty, but are filled with subtle, moving energy shaped by the invisible forces of electromagnetism, turning the void into a vibrant, glowing web. Giant nebulae, the vibrant, colorful nurseries of the arms. Throughout the spiral arms of the Milky Way lie vast, glowing nebulae, enormous clouds of gas and dust that are among the most beautiful sights in the universe. These nebulae are lit by the presence of young, massive and incredibly hot stars that have just formed within them. These stars emit intense ultraviolet light that energizes the surrounding hydrogen gas, causing it to shine with vivid, glowing colors. In these H2 regions, hydrogen glows in soft, romantic reds, while oxygen can produce gentle greens or deep blues, creating a celestial palette of light. These glowing clouds are the true birthplaces of stars. Inside them, the process of creation is happening right now, as dense pockets of gas collapse into new suns. The shapes of nebulae are sculpted by the powerful stellar winds and radiation of the stars they nourish, forming arches, pillars, towers, and cavities that create some of the most striking landscapes in the cosmos, such as the famous Pillars of Creation. Studying these nebulae helps astronomers understand the chemical makeup of the galaxy and the processes that lead to the formation of solar systems like our own. They fill the Milky Way with soft, colourful light, transforming ordinary gas into radiant, living sculptures of starbirth, a reminder that the galaxy is constantly creating itself anew in bursts of colour and light. Brown dwarfs, the elusive, failed stars of the galactic disk. In the vast population of the Milky Way, there exists a class of objects that fills the quiet, mysterious space between the largest planets and the smallest stars. These are the brown dwarfs, often referred to as failed stars. They form from collapsing clouds of gas just as stars do, but they never gather enough mass to reach the critical temperature and pressure needed to ignite full, steady nuclear fusion in their cores. Because they lack this internal engine, brown dwarfs do not shine with the brilliant light of a sun. Instead, they glow only faintly in the infrared, releasing the leftover heat from their formation. They can have masses many times that of Jupiter, yet they remain cool and dim, drifting quietly and almost invisibly through the galactic disk. These elusive objects are incredibly difficult to detect, yet they are thought to be very numerous, adding a hidden layer of mass and complexity to the galaxy. Their atmospheres contain unusual molecules and exhibit weather patterns, such as clouds made of molten iron or hot sand that shift over hours or days. Studying brown dwarfs helps astronomers understand the lower limits of star formation and the diversity of objects that can form in the cosmic dark. They are the quiet, shadowy cousins of the stars, reminding us that not every celestial body fits neatly into a simple category, and that the galaxy is filled with hidden worlds that burn with a dim and lonely light. Lava oceans, the molten, scorching vistas of the inner systems. Among the many extreme environments found in the Milky Way, few are as hellish or as fascinating as the lava worlds. These are rocky exoplanets that orbit so incredibly close to their parent stars that their surfaces are heated to thousands of degrees, preventing a solid crust from ever forming or melting it back into a liquid state. On these worlds, the landscape is not made of rock and soil, but of churning, glowing oceans of molten stone. Rivers of lava flow under the intense pull of the star's gravity, and volcanic activity is a constant planet-wide event. The temperatures on the day side of these planets are high enough to vaporize rock itself, creating a thin atmosphere of mineral vapor that can condense and fall as rock rain on the cooler night side. These lava worlds are often tidally locked, meaning one side always faces the star's scorching heat, while the other faces the cold of space, creating a world of extreme contrast. Studying these planets helps astronomers understand how worlds evolve under the most intense radiation, and how the building blocks of planets behave at their thermal limits. They offer a glimpse into a cosmic landscape forged by heat and motion in the harshest possible conditions, a place place where the very ground beneath your feet is a glowing, liquid sea of fire. Molecular reservoirs. The fertile grounds of the galactic center. Deep within the central regions of the Milky Way, surrounding the supermassive black hole, lies an enormous and dense reservoir of molecular gas. This material is cold, rich in complex molecules, and contains the essential ingredients needed for the formation of new stars and potentially life. However, this is not a quiet or simple place. The galactic center is a region of extremes. Strong radiation fields from nearby massive clusters, turbulent motions from the galactic rotation, and the intense gravitational pull of Sagittarius A star affect the gas constantly, stretching and compressing it. Yet, within this chaos, pockets of gas remain shielded enough for molecules like water, ammonia, and even complex organic compounds to survive and grow. These regions form some of the most massive and active star-forming sites in the entire galaxy, proving that even the most intense and dangerous environments can be fertile grounds for creation. Observing these molecular reservoirs requires using radio and infrared wavelengths that can penetrate the thick, obscuring dust of the core. They reveal how the galaxy maintains its life cycle, even in its most crowded and violent neighborhoods, showing that the heart of the Milky Way is not just a place of destruction, but a cradle for the next generation of cosmic structures. Double planet systems, the graceful waltz of twin worlds. In the vast variety of the Milky Way, not all planets follow the simple path of revolving around a single star in isolation. In rare and elegant cases, two planets of similar mass can form close enough to one another that they become gravitationally bound, sharing a mutual orbit around a common center of gravity between them while they both travel around their sun. These double planet systems move through space like partners, performing a slow and graceful dance. Their shared motion creates complex patterns of tides, rotation, and lighting that would be unlike anything experienced on a single planet world. From the surface of one planet, the other would appear as a massive, detailed presence in the sky, much larger and closer than our moon appears to us. Finding such systems is a significant challenge for modern astronomers, as they often resembled single planets when viewed from vast distances. However, detailed observations of their orbital variations can reveal their dual nature. These systems provide vital insight into how planets form and interact in the early years of a solar system, showing that worlds can develop in cooperative pairs rather than solitary paths. The existence of such arrangements adds a touch of elegance and beauty to the varied structures of the galaxy, proving that gravity can create harmony as well as chaos. Supernova remnants. The vibrant, glowing aftermath of death. When a massive star reaches the end of its fuel and collapses, it dies in a supernova, the most powerful explosion in the universe. But the story of the star does not end with the flash of light. It leaves behind a supernova remnant, a massive, expanding cloud of gas and debris that can grow to be hundreds of light years wide. These remnants continue to glow for thousands of years, long after the original explosion has faded from view. Shock waves from the blast heat the surrounding interstellar gas to millions of degrees, causing it to emit X-rays, radio waves, and visible light in intricate filament-like patterns that look like celestial lace. Within these remnants, the heavy elements forged in the heart of the dying star, iron, gold, and uranium, are dispersed into the galaxy, where they will eventually become part of new stars, planets, and even living beings. Studying these remnants helps astronomers understand how the chemical landscape of the Milky Way is built and how energy is distributed through the system. Each remnant is a colorful, glowing marker of a life that ended in brilliance, a vibrant reminder that in the galaxy, death is always a source of new life and new complexity. They are the beautiful ghosts of the cosmic giants, drifting forever in the starlit dark. Red-hot worlds, the scorching survivors of proximity. In the diverse and often extreme inventory of the Milky Way, there are planets that orbit so incredibly near their parent stars, completing a year in just a few days or even hours, that their surfaces are heated to temperatures that defy the concept of a world. These are the red-hot worlds, planets that exist on the very edge of being consumed by their suns. These close-in planets are often massive gas giants, known as hot Jupiters, or large rocky worlds whose atmospheres have been transformed by the intense radiation. The heat is so great that it can cause the planet's atmosphere to swell and shimmer, sometimes giving the entire world a reddish, golden, or even violet hue. On these worlds, the dayside temperatures can be high enough to melt lead or vaporize iron, creating exotic atmospheric chemistries where it might rain molten glass. The intense stellar winds from the nearby sun constantly strip away the upper layers of the planet's atmosphere, forming long, comet-like tails of gas that trail behind the world for millions of miles. Studying these scorching survivors reveals how planets adapt to the harshest possible environments and provides valuable clues about the limits of planetary survival. They show that the Milky Way is home to worlds that are far more extreme than anything found in our own solar system, places where the very air is a glowing testament to the power of the stars. Icy crystals, the frozen, silent incubators of space. In the coldest, most sheltered regions of the Milky Way, far from the intense, scorching heat of young stars or the violent radiation of the core, clouds of gas can become cold enough for molecules to freeze. In these dark, silent places, tiny dust grains become coated in delicate layers of ice, forming microscopic crystals of water, carbon dioxide, methane, and ammonia. These icy crystals are not just frozen waste. They are the silent, essential incubators of cosmic chemistry. Their surfaces provide a place where atoms can meet and react, gradually building up the complex organic molecules, the building blocks of life, that will one day contribute to the formation of comets, asteroids, and planets. Infrared observations can detect the presence of these ices by the way they absorb specific wavelengths of light, revealing the hidden treasures within the dark nebulae. Studying these frozen clouds helps astronomers understand the earliest, most delicate stages of star and planet formation, showing how the galaxy prepares the ingredients for future worlds in its quietest corners. They remind us that the Milky Way is a place of infinite patience, where the complex chemistry of existence unfolds slowly, one molecule at a time, in the frozen silence of the dark. Red giants, the ancient, swelling factories of life. Red giants represent a late and spectacular stage in the life of many stars, including our own sun in the distant future. As a star exhausts the hydrogen fuel in its core, its internal balance shifts, causing it to expand to hundreds of times its original size and cool, turning a brilliant deep red color. Inside these vast, bloated envelopes, the star begins to forge new, heavier elements through nuclear fusion: carbon, nitrogen, and oxygen. Over time, red giants become unstable, pulsing with energy and shedding their outer layers in slow, steady stellar winds that carry these newly created elements far into the interstellar medium. This material becomes part of the great cycle of galactic recycling, providing the building blocks for the next generation of stars, planets, and, eventually, life. In this way, red giants act as the ultimate factories of the Milky Way, enriching the galaxy with the ingredients necessary for complexity. Observing them helps scientists understand the chemical evolution of our home and the long-term fate of stellar systems. Their gentle, crimson glow is a reminder that even as a star nears the end of its luminous journey, it is still contributing to the future of the cosmos, ensuring that its legacy is woven into the very fabric of the next world to be born. Extreme orbits, the chaotic, elliptical paths of eccentric worlds. Not all planets in the Milky Way follow the neat, nearly circular orbits that we see in our own solar system. Many worlds travel on extreme orbits, stretched elliptical paths that carry them on a wild journey between two total opposites. These eccentric planets may spend half their year in the freezing, starless dark of their system's outer reaches, only to swing inward and skim the scorching surface of their sun at incredible speeds. The seasonal changes on such worlds would be catastrophic and profound. When far from the star, the entire planet might freeze solid, with its atmosphere condensing into frost on the ground. As it hurtles toward its close approach, the temperature would rise by thousands of degrees in a matter of weeks, causing the ice to boil away and the atmosphere to expand in violent planet-wide storms. These extreme orbits often form through chaotic gravitational interactions, perhaps a close encounter with another large planet, or the pull of a distant companion star. Studying these wild paths helps astronomers understand the turbulent history of planetary systems and how orbits can change over time. They reveal that the stability we enjoy on Earth is a rare and precious gift in a galaxy filled with worlds that must survive a yearly cycle of fire and ice. Primordial hydrogen, the unchanged relics of the beginning. Scattered throughout the vast arms and the lonely halo of the Milky Way are pockets of primordial hydrogen, clouds of gas that have remained largely unchanged since the very earliest eras of the universe. This is the raw material that existed before the first stars were ever born, long before the galaxy had settled into its current spiral shape. While most of the hydrogen in the Milky Way has been processed through the hearts of stars and enriched with heavier elements, these primordial areas preserve a simpler, ancient chemistry. They are the artifacts of the Big Bang itself, drifting silently through the galaxy for over 13 billion years. These clouds are typically cold, faint, and incredibly difficult to detect, yet they play a vital role by slowly feeding fresh material into star-forming regions, ensuring that the galaxy can continue to create new suns. Studying them allows scientists to compare the modern galactic environment with the conditions of the ancient past, helping us trace the long and complicated history of how the Milky Way grew from a small, irregular clump of gas into the majestic spiral we call home. They are the quiet, enduring reminders of our collective beginning, still present in the dark corners of the sky. Silent collapses, the quiet, hidden endings of the giants. We are often told that massive stars end their lives in the brilliant, world-shaking explosion of a supernova. But nature is rarely so simple. Astronomers have discovered that some massive stars choose a different, more mysterious path: the silent collapse. In these events, the star reaches the end of its life, but instead of exploding outward, it simply collapses directly inward, vanishing from the sky with little to no visible disturbance. This happens when the internal structure of the star fails so rapidly and completely that the core forms a black hole instantly, pulling the outer layers of the star down into the abyss before they can be blasted away. The star simply blinks out of existence, leaving behind only the invisible pull of a new black hole. These silent endings are incredibly difficult to observe, but astronomers search for missing stars, stars that were clearly visible in older surveys but have vanished without any record of an explosion. These events reveal a more complex and subtle landscape of stellar death, where the final moments of a star's life depend on a delicate balance of mass, rotation, and magnetism. They remind us that in the Milky Way, not everything ends in fire. Some things simply fade into the dark, leaving only a shadow where a sun once shone. Chaotic birth. The turbulent systems of multiple stars. While we enjoy the stability of a single sun, many planetary systems in the Milky Way are born into much more chaotic environments, the systems of multiple stars. Imagine a world born into a cluster of 3, 4, or even more suns, all bound together by gravity in a complex, shifting dance. These environments are filled with competing gravitational tugs that make the process of forming a planet incredibly difficult and unpredictable. In these systems, the protoplanetary disks of gas and dust are often twisted, tilted, or torn apart by the passage of nearby stars. Planets that do manage to form must find a stable path through a field of shifting forces. Some end up orbiting a single star, while others find a wide path that circles the entire group. Many are not so lucky and are flung out of the system entirely to become rogue planets. The worlds that survive face a sky of constant change, where day and night are determined by the complex geometry of several suns. Studying these chaotic systems helps astronomers understand the full range of planetary birthplaces and the resilience of nature. They show that planetary birth is not limited to orderly, quiet neighborhoods, but can occur even in the midst of disorder and constant cosmic change, proving that life can find a way even under the most restless of skies. Star-forming filaments, the long, glowing threads of creation. In the most active regions of the Milky Way, the birth of stars does not happen in isolated clumps, but along enormous, elongated structures called star-forming filaments. These are long, narrow threads of cold, dense gas and dust that can stretch for hundreds of light years across the spiral arms, looking like glowing veins in the body of the galaxy. These filaments act like cosmic conveyor belts, feeding material into the dense nodes where new stars are taking form. Gravity pulls the gas inward along the length of the filament, creating a series of regularly spaced pockets that collapse into stars. A process that looks like beads being strung on a thread of light. Observing these structures helps astronomers understand how large-scale processes in the galaxy, such as the rotation of the disk or the passage of shock waves, guide the birth of stars on a local level. They reveal a sense of order and organization in the apparent chaos of the interstellar clouds, showing that the galaxy has a structure and a rhythm to its creation. These filaments are the architecture of the future, the glowing blueprints for the next generation of suns that will one day light up the night. Isolated stars, the solitary, lonely sunsets of the halo. While the majority of stars in the Milky Way are born in crowded clusters or busy spiral arms, there are some that live their entire lives in near-perfect isolation. These isolated stars are found in the far reaches of the galactic halo or in the deep gaps between the spiral arms, where their nearest neighbor might be hundreds of light years away. Their environments are calm, silent, and free from the radiation or gravitational disturbances of other stars. If such a star has a planet, its sky would be a deep, absolute black, with only the distant, hazy glow of the Milky Way to light the night. These solitary suns rarely interact with other objects, allowing them to evolve in total peace. Studying them provides a unique control group for astronomers, allowing us to see how a star grows and ages without any outside influence. Their isolation reveals the wide variety of environments that exist within our galaxy, from the bustling metropolises of the core to the lonely homesteads of the outer edges. They remind us that even in a structure as crowded as a galaxy, there is still room for solitude, and that a sun can shine brilliantly even when it has no one to see it but the void. Exotic atmospheres, the glowing chemistry of rare suns. Certain stars in the Milky Way are not made of the usual mix of hydrogen and helium. Instead, they display chemical signatures that are truly exotic, containing high amounts of rare elements like carbon, zirconium, strontium, or even technetium, an element that does not occur naturally on Earth because it decays so quickly. These exotic stars are the chemical treasures of the galaxy. Their unusual atmospheres are created through rare and complex nuclear processes, often involving the merging of stars or the transfer of material from a dying companion. Some of these stars are carbon stars, which burn with a deep, haunting crimson light because their carbon-rich atmospheres absorb all the blue starlight. Others are the remnants of ancient collisions between neutron stars, which forged the heaviest elements in the universe. Studying these stars helps astronomers trace the long and complicated pathways through which the building blocks of life and technology spread across the galaxy. Their distinctive chemical fingerprints act as clues to events that happened billions of years before the Sun was even a thought in a molecular cloud. They show that the Milky Way is a place of incredible chemical diversity, a celestial laboratory where every element has its own story to tell. Dark matter, the invisible scaffolding of the galaxy. Beyond the stars, the gas and the dust, lies something far more mysterious. Scientists have realized that the Milky Way is far heavier than it appears. The stars we see and the gas we map only account for about 10 to 15% of the total mass of the galaxy. The rest is made of an invisible substance called dark matter. Dark matter does not emit, absorb, or reflect light. We cannot see it with even our most powerful telescopes. We only know it is there because of its gravitational pull. It acts as an invisible scaffolding, a massive halo that surrounds the galaxy and prevents the stars in the outer arms from being flung away by the speed of their rotation. Without dark matter, the Milky Way as we know it would not exist. It is thought that dark matter was the first thing to form in the early universe, pulling together the gas and dust that eventually became the first galaxies. Every shimmering star and glowing nebula we see is like foam on a dark, invisible ocean. Studying this mystery is one of the greatest challenges in modern science. It reminds us that for all our knowledge, most of the universe remains hidden from our eyes, a vast, silent secret that holds the stars in its hands. The future collision, Milky and the fate of the night. The Milky Way is not stationary. It is moving through space at hundreds of thousands of miles per hour, heading on a direct collision course with our neighbor, the Andromeda Galaxy. Right now, Andromeda is just a faint smudge in the sky, but it is coming closer every second. In about 4 billion years, the two galaxies will meet. They will not crash like solid objects. Because there is so much empty space between stars, individual stars will likely pass each other by. Instead, gravity will perform a violent and beautiful dance. The spiral arms will be torn apart, stretched into long tidal tails. New stars will burst into life as the gas clouds collide and compress. Eventually, the two galaxies will merge into one giant elliptical galaxy, often called Milky. The familiar band of the Milky Way will disappear from the sky, replaced by a brilliant, glowing core of older stars. This is the ultimate fate of our home, a transformation that will create a new world from the remnants of the old. It is a reminder that in the cosmos, even the most massive structures are temporary, part of an ongoing cycle of change and rebirth. The life cycle of galaxies, from spirals to giants. The evolution of the Milky Way is part of a larger story of how all galaxies live and die. Galaxies begin as small clumps of matter, drawn together by dark matter in the early universe. As they grow, they acquire the gas needed to form stars, often taking on spiral shapes like our own. These spirals are vibrant and active, the youth of the galactic world. Over time, through collisions and mergers, these spirals can lose their structure. As they use up their gas and stop forming new stars, they become elliptical galaxies, huge, smooth spheres of older, redder stars. This is the old age of a galaxy. Eventually, after trillions of years, even these stars will fade and die, leaving behind dark remnants like black holes and cold husks of matter. The Milky Way is currently in its prime, a vibrant, middle-aged spiral filled with light and activity. But the process of aging is always underway. By understanding the life cycle of other galaxies, we can see our own future written in the stars. It is a slow, majestic progression from light to dark, a journey that spans the entire history of time itself. The Great Attractor, the pull from beyond. Our galaxy is not just moving toward Andromeda. The entire local group, including the Milky Way and dozens of other galaxies, is being pulled toward a mysterious point in space called the Great Attractor. This is a region of immense gravitational force, located about 220 million light-years away. Because the Great Attractor lies behind the zone of avoidance, a part of the sky hidden by the thick dust of our own galaxy, we cannot see exactly what it is. It is likely a massive cluster of galaxies, so heavy that its gravity reaches across millions of light-years to tug on everything in its neighborhood. This pull is part of the cosmic flow, the movement of galaxies through the web of the universe. It reminds us that even as we journey through our own galaxy, the entire Milky Way is part of a much larger structure, being drawn toward a distant, invisible destiny. We are travelers on many scales, moving within our solar system, within our galaxy, and within the universe itself. The Fermi bubbles, the giant ears of the core. In 2010, astronomers discovered something truly bizarre, stretching above and below the center of our galaxy. Two massive bubbles of gamma radiation, each extending 25,000 light-years into space, rise from the galactic core like giant ears. These are the Fermi bubbles. These bubbles are the evidence of a violent episode in our galaxy's past. They were likely created by a massive outburst from the central black hole, Sagittarius A star, perhaps millions of years ago, when it consumed a large amount of gas or stars. This event released an incredible amount of energy, blowing a hole in the galactic gas and pushing material out at millions of miles per hour. The Fermi bubbles are invisible to our eyes, but in gamma rays, they are some of the largest structures in the Milky Way. They are a haunting reminder that our invisible monarch at the core is not always quiet. It has a history of powerful outbursts that can shape the space far beyond its immediate grasp. Stellar nucleosynthesis, the forge of the elements. Every atom in your body, from the iron in your blood to the calcium in your teeth, was created inside a star in the Milky Way. This process is called stellar nucleosynthesis, the cosmic alchemy of the universe. Stars begin by fusing hydrogen into helium. As they age and grow hotter, they forge heavier elements: carbon, oxygen, neon, and silicon. The heaviest elements, like gold and uranium, are created in the final violent moments of a star's life, during supernova explosions or the collision of neutron stars. When these stars die, they scatter these elements into space, where they become part of the gas clouds that form the next generation of planets and life. We are, quite literally, made of star stuff. The history of the Milky Way is written in our very bones. Every time you breathe, you are inhaling the legacy of a star that lived and died billions of years ago. It is a profound connection that binds us to the very heart of the galaxy. Gravitational waves, the ripples in the dark. For a long time, we could only study the Milky Way through light. But now, we have a new way to listen to the galaxy: gravitational waves. These are ripples in the fabric of space-time itself, created by the most violent events in the cosmos, such as the collision of black holes or the merger of neutron stars. As these ripples travel through the galaxy, they stretch and compress space by an amount so tiny it is almost impossible to measure. But with sensitive instruments like LIGO, we can detect these whispers from the dark. They allow us to hear events that produce no light, revealing a hidden side of the Milky Way. Instruments like LIGO, we can detect these whispers from the dark. They allow us to hear events that produce no light, revealing a hidden side of the Milky Way. Gravitational waves are the music of the spheres, the vibration of the galaxy itself as it undergoes dramatic changes. They tell us about the hidden population of black hole binaries and the final moments of massive stars. By listening to these ripples, we are gaining a deeper understanding of the forces that move the stars and shape the void. Techno-signatures, the search for company. As we journey through this vast river of starlight, it is impossible not to wonder, is anyone else out there? The Milky Way contains hundreds of billions of stars, and we now know that most of those stars have planets. In such a vast system, the possibility of other civilizations feels almost inevitable. Scientists are searching for techno-signatures, signals or structures created by advanced technology. This could be a stray radio signal, the flash of a laser, or the presence of massive structures like Dyson spheres that capture the energy of a star. So far, the silence has been absolute. This is the Fermi paradox, the contradiction between the high probability of alien life and the lack of evidence for it. Perhaps we are truly alone, a rare spark of consciousness in a silent galaxy. Or perhaps we are simply the first to look. The search for company is part of our journey, a quest to find our place in the cosmic family. Even if we never find a signal, the search itself enriches our understanding of what it means to be human in a universe so large. The Kardashev scale, the energy of a civilization. When we think about advanced civilizations in the Milky Way, we often use the Kardashev scale to measure their power. This scale ranks civilizations by the amount of energy they can control. A Type 1 civilization can control all the energy of its home planet. We are not yet at this level. A Type 2 civilization can capture the entire energy output of its sun, perhaps by building a massive shell around it. A Type 3 civilization, the ultimate masters of the galaxy, can control the energy of an entire galaxy like the Milky Way. In such a scenario, the entire galaxy would be a living structure, shaped by the needs of its inhabitants. Looking at the Milky Way, we see no obvious signs of such activity. The light we see is natural, the product of stellar physics rather than engineering. It suggests that if advanced civilizations exist, they are either rare or have found ways to live in harmony with the natural light of the stars. The zone of avoidance, the hidden half of the sky. There is a part of the universe that we cannot see, simply because our own galaxy is in the way. This is the zone of avoidance. Because the disk of the Milky Way is filled with so much dust and gas, it acts as a permanent blind spot, hiding the galaxies and structures that lie behind it. Astronomers must use infrared and radio telescopes to see through this wall, but even then, our view is limited. This is where the great attractor hides, pulling on us from the darkness. It is a reminder that even our home has its secrets. No matter how much we map the sky, there will always be parts of the universe that remain a mystery, hidden by the very stars that give us light. The Magellanic Stream, the trailing tail of our neighbors. Trailing behind our satellite neighbors, the large and small Magellanic Clouds, is an enormous ribbon of gas called the Magellanic Stream. It stretches across nearly half of the sky, a long tail of hydrogen gas pulled out of the clouds by the gravity of the Milky Way. This stream is like a trail of breadcrumbs, showing the path our neighbors have taken as they orbit us. It is also a source of food for our galaxy. Over time, this gas will fall into the Milky Way, triggering new bursts of star formation. It is a reminder that the relationship between galaxies is one of constant exchange, a physical interaction that shapes the structures we see and the stars that will be born in the future. The life cycle of a star, from dust to dust. Every star in the Milky Way follows a predictable life cycle, a journey from the stillness of a nebula to a final, often violent, end. This journey is determined entirely by one factor: the star's mass. Stars like our Sun burn steadily for billions of years, fusing hydrogen into helium. When they run out of fuel, they expand into red giants, shed their outer layers as planetary nebulae, and leave behind a white dwarf, a cold, dense husk of carbon and oxygen. Massive stars live much faster. They burn through their fuel in a few million years, explode as supernovas, and collapse into neutron stars or black holes. This cycle is the fundamental engine of the galaxy. It creates the elements, recycles the gas, and powers the light. Every star you see is at some point in this journey, some just beginning as protostars, others in their steady middle age, and some nearing the end of their luminous lives. It is a beautiful, rhythmic process that has been repeating for billions of years, a constant pulse of creation and destruction. The void of Boötes, a contrast in darkness. To truly appreciate the richness of the Milky Way, we must compare it to the void of Boötes. This is a vast region of space, 250 million light-years across, that contains almost nothing. While the Milky Way is part of a crowded neighborhood, the void of Boötes is a desert. If our galaxy were at its center, we would have seen no other galaxies until the 1960s. Our home is a place of abundance. We are surrounded by stars, gas, and neighbors. The richness of the Milky Way is what allowed life to emerge, providing the heavy elements and the energy needed for complexity. Looking at the emptiness of the voids makes the glowing band of our galaxy feel even more precious, a rare island of light and matter in an unimaginably empty universe. Conclusion: the eternal silence and the soft glow. Thank you for spending this monumental, quiet time beneath the vast, ancient canopy of the Milky Way tonight. As we reach the end of our journey through this silent giant, let the thought of that great river of starlight linger gently around you. It is not just an object to be studied from a distance or a map to be followed through the night. It is a calm, enduring presence that has watched over the Earth for 4 billion years and will continue to do so long after our own light has changed. The galaxy remains there in the background of your mind now, silent, steady, and vast, like a soft glow behind closed eyes. As you settle into the quiet of your own room and your own world, imagine the slow, relentless drift of those hundreds of billions of suns far overhead, each carrying its own worlds, its own history, and its own unique light. Imagine the hush between them, the deep, velvet stillness that fills the enormous spaces where light takes its time to travel across the centuries. If you feel your eyelids growing heavy, allow the grand story of life on Earth to wrap around you gently and guide you into calm. Don't forget to subscribe to listen to more of our bedtime stories. Close your eyes, take a deep breath, and slowly drift into sleep, into silence, into the boundless, timeless current where all life intertwines. Wishing you a quiet, comforting night.